Hi everyone, my name is Haoyi, and this presentation is about Java build tools. So no AI in this presentation. I feel like the only one not talking about AI this year. But the motivation for this talk is that although Java is known to be very easy to learn, very performant, and have very good IDE support, Java build tools like Maven or Gradle often don't live up to that expectation. So in this talk, we'll look at why are these build tools hard from a user perspective, but also why are these build tools hard from an implementer or maintainer perspective? Like why doesn't someone just go make a better build tool tomorrow and fix all the user-facing problems? We'll talk about one of my open source projects called Mill, which try to explore this problem space. And one of the interesting ideas behind Mill, which is this idea of object-oriented builds, which really simplifies how these build tools work. So first, a bit about myself. I've been programming Java for 20 years. I've been doing open source projects since about 2012 or 2013. My last job was at Databricks, which is a Scala on the JVM shop. So a lot of these projects are Scala, but also many Java and other JVM technologies. My professional work is all developer tools. So dev environments, CI testing, ID integrations, and build systems, which is what I'm going to talk about today. First, why are build tools hard from a user perspective? I think that largely comes down to the three areas I mentioned: performance, ID support, and usability. So first, talking about performance. Java tooling doesn't have a reputation for being fast or snappy. And when you look at the numbers, this actually is not surprising. So for example, if you take the Netty code base, Netty is an open source networking framework popular on the JVM ecosystem. It's about 500,000 lines of code, not a small project. It takes about 50 seconds to compile on my MacBook Pro. I'm going to kick this off now so you can see it. So I'm just going to copy paste this over to my terminal. I'm doing a clean compile, so everything's from scratch. And I'm not going to wait for it because it'll take a while. So this is about how fast the experience of working with Java is. It takes 5 seconds, 10 seconds, 20 seconds, 50 seconds. Even compiling a single module like the Netty common module, that's one of the smaller modules within Netty code base, takes about 4 to 5 seconds to compile. So you look at this, and this feels kind of slow and not very responsive. But what people don't realize is that if you take the command that Maven's calling internally, you call Maven --debug, and it prints out the command it's going to run, and it turns out this is a command. I shrunk the class part a bit so you can fit on the slide, but it's basically called javac with -d -cp and a list of source files. It actually compiles 3 times faster than when using Maven. And this is just compilation, like everything's already downloaded in cache, all the dependencies are already on disk. I'm just compiling things, but Maven adds about 3x overhead over just calling javac directly. And if any of you have worked with Java for a long time, you may know that calling javac directly is the worst possible performance you can get from javac, because javac is a JVM application, and JVM applications are known to have cold starts and warm up and get performant later. So when you call javac like this, all you're measuring is like worst case cold start. So what happens when you warm it up? So I have a small benchmark that does this. And what you find is that you get another 5 times speed up over the cold version of javac, which is what you expect, right? Warm Java is really a lot more faster than cold Java by about 5 to 6x. So now we are looking at 15 times faster than Maven, and we didn't do anything special. We didn't rewrite the Java compiler in Rust. Our build tools not written in Rust or anything. We just took the same Java compiler with the same source files and ran it properly as a warm JVM process rather than as a cold JVM wrapped in a whole bunch of other cold JVMs. So I can show you this live. Earlier, I kicked off the Netty clean compile, took about a minute or so on my laptop. Let me move this closer so it's easier. If I run the single module compile of the Netty common, so it'll take about 4 to 5 seconds. Here it took 4.8 seconds. If I run this very long javac command, you're not going to type this out yourself, but just say you have a script that does it for you. It takes 1.4, 1.5 seconds. And if I run this java bench.java file, which is a single file Java application, just runs a while loop. I can show it to you here. Where is it? So all this does is it's a main method, a while true loop, and it runs a Java compiler over and over. You see, it started off a bit slow, but after running for a few iterations and it warming up, it's now taking maybe about 300-ish milliseconds to compile the same 29,000 lines of code. It just now took 4.5 seconds. So it's literally a 15 times speed up. So compiling Java isn't the only thing you do day to day in your workflow, but it just shows how much overhead and how much surprising overhead that build tools might add over what's actually under pretty fast and performant underlying platform. So if people's experience working with Java was it took 0.3 seconds to compile their code rather than 4.5 seconds, I think the reputation of Java as a slow or sluggish development experience would be very different from what it is today. So the next thing I'm going to look at is IDE experience. So Java is famous for having great IDEs. All the build tools have IDE integrations, and it works very well, but often only at a superficial level. So if I open up this example I have here is, no, this one. So this is the Mockito code base. So Mockito is a popular open source unit testing library for creating mocks and fakes and stuff in your unit tests. It's a Java project built using Gradle. In this case, I'm looking at the Gradle Groovy syntax of the Mockito error-prone submodule. So you see this does have syntax highlighting. I do have some IDE assistance here. You can see some inline hints in IntelliJ here. So there is IDE support. But when you try to actually use your IDE to navigate around and learn things, for example, let's say I want to find out what was JVM args before I appended the value to it. That seems very reasonable. You may try jumping to it. You see that you get this getter and setter, and you get nothing interesting here. You can't see the value that was there before. You can't see where this value is being used later on. You can't see the Java doc or anything. And it's just, you just kind of hit the wall. Like you technically have jumped to definition, but it doesn't actually give you anything useful. And it's not just JVM args. So compiler args, you also get these stubs. Test implementation, you also get these stubs. So although all these build tools technically have IDs for you, technically can jump around your build system, it's practically so useless that it might as well not exist. And this is in stark contrast to the IDE support of any actual Java code. Like if I open up this random test file within the Mockito code base, anything within this file, I can jump to it and find something useful, and jump to something and find something useful, and jump to it and find something useful. So that's maybe surprising, and just given that people expect such a good experience working in your Java code, and then you go to your Mockito, your Gradle build or Maven build, and the IDE support just falls off a cliff. So I showed you the Gradle Groovy syntax. The Gradle Kotlin syntax has the same problem. The Maven XML syntax has the same problem. If you don't know what exec or what property regex means, there's nothing your IDE can do to help you understand what these things do. Last thing I'm going to talk about is a usability angle. So there are two aspects to usability. There's small scale usability and large scale usability. I'll go through both. For small scale usability, let's say I have this small program, like it's a programming interview, you try and get a job. Someone asks you to write a web crawler, and then they're going to make you parallelize it and stuff just for the interview problem. Here we have a main method. We have a breadth first search over here that has a for loop that goes layer by layer and collects the next articles and then swaps current with next and then does another traversal. And then for each article, it calls this fetch links method, which connects to Wikipedia using this JSoup library and scrapes from the HTML to get the main HTML tag, the paragraph, the links, get all the href links, and grab them to be the next set of outgoing set crawl. So this is relatively simple. This is a very small program. If it was any smaller, if it didn't have this JSoup dependency, you could just run it using Java, like foo.java from the command line. But because we have this JSoup dependency, we cannot just run it. We need the build tool. Let's say you have Maven or Gradle, and who here knows how to type out the XML for configuring Maven without copy pasting it from Stack Overflow or ChatGPT or Google? Like, just can't, right? So even for such a simple program, you're not going to write this script in Java, not because the Java code is complicated. The Java code is actually quite nice and easy. Nowadays, you even have type inference with vars and stuff, so you don't need to duplicate the type signatures everywhere. But because you're not going to want to have to deal with all this kind of boilerplate Maven just to write a small script. So people write these scripts in Python or in Bash purely because of Java's build tool overhead. Even running the script in Java is quite annoying. You can't just say Maven like HTML scraper.java. You have to say Maven exec -Java -g exec.args equals open quote, and then the arguments, in this case, maybe Singapore and one. So that's a small scale usability. Java build tools often have a large-scale usability problem as well. So, for example, in the large projects, you often have to customize your build. Like in Netty, they have to customize it to compile some C code for native performance. For Mockito, they have to do some bytecode mangling or modifications for the to make the mocks work. So let's say I have this strawman requirement. I want to save the project line count as a TXT resource file for use at runtime. So it's a bit artificial, but just representative of the many things people need to do in their build systems. Doing this in traditional Java build tools is not hard. It's not impossible, but it can be surprisingly tricky. So here's a simple example of configuring this using Maven's exec plugin. And there are two bugs here. And let's see if anyone can spot them. So there's like the simplest Maven config customization in the most popular Java build tool in the world. Like this is literally a hello world customization. It doesn't get simpler than that. And there are two bugs. And no one can spot it realistically. So one of the bugs is we forgot to escape our ampersands because it's not just bash in XML, because it's not just bash, it's bash in XML, and XML doesn't allow you to use ampersands without escaping them with ampersand AMP semicolon. Similarly, we need to escape our little greater than sign here because this is a XML special character. And the other things, it doesn't work on Windows. Anyone who has colleagues working on Windows, this will break because Windows doesn't have SH, and then many other issues. So that's Maven. Gradle has a different set of problems. Gradle, you don't have Windows problems because it runs on JVM in Kotlin or Groovy. You don't have XML escaping problems, but you still have a lot of trickiness in the Gradle config. So this Gradle config also has a bug that probably no one here will be able to spot, which is that we have registered the wrong folder as input folder here. So we registered the source main folder as input, but we actually only care about source main Java, which means that if you touch source main resources, you touch source main templates, or you touch source main config, it will rerun this task even though the output will have not changed, which just means your build will be non-deterministically slower sometimes for reasons no one can catch. And you won't catch it by testing because the output will be correct. You won't catch it at code review because none of you could catch it. Your colleagues won't catch it. Your plugin authors won't catch it. And so this is how build systems tend to get slow, flaky, and broken over time because it's so hard to configure them correctly. And it's so easy to make mistakes. And that's why people have this reputation or rule of thumb that you don't touch your build system. It's scary and you will screw it up. So that's why build tools are hard for users, right? Like the performance sucks compared to how fast it could be, literally 15 times slower than it should be. The ID support is not great compared to Java, what you expect. And usability, both for small projects and for large projects, is problematic. So if there's so many problems, why don't people just make a better build tool and fix all of these? I think the answer to that is that build tools are also very hard for the implementers of these tools as well, not just for the users. So every build tool starts off relatively simple. Like if any of you have used this JBang project, which lets you run these small Java single file projects, you just put some magic comments at the top saying what dependencies you have and just run it. It's very easy, very simple tool. But as a project gets more complicated, you have multiple modules, you have lots of different config options. Having this huge flat list of key value pairs doesn't cut it anymore. Often you end up having some kind of hierarchy. So this is like the GitHub Actions config, which can kind of thought of as a build tool. You can see it's a bit more structured and there's a big list of key value pairs. But when you look at this a bit more closely, you realize it's not just a hierarchy. Like I'm actually passing in arguments to what looks like functions that are being used in the function body. I am declaring build thing here. I'm referencing it in my test job. I am defining this shared.yaml template. I'm inheriting it in these other jobs. So when you think about this more deeply, it's not actually a hierarchy you care about, but a graph. And I think that's what makes these build tools very complicated because every build tool is all about defining these templated graph computations. So for example, if you have three modules like in the bottom here, you'll see that each module has assembly, each module has a compile step, each module has sources. They look very similar, but not quite the same. Some of them don't have an upstream class part, some of them do. Some have different compiler flags or runtime flags. So you need a graph because the tool needs to order and parallelize what steps to run before and after or in parallel. You need computations because class files and jar files don't create themselves. Someone in Java or Kotlin or Bash or Groovy needs to say how it's created. And it needs to be templated because the different modules or different parts of your build larger project are often very similar, but not quite the same. So there's lots of different ways to do this. Like GitHub Actions does this with needs keys for the graph, bash snippets for computations, and curly braces for templating. There are a million and one different syntaxes you could imagine to define these templated graphs. And even if you don't have to do it, the plugin authors have to do it. And that doesn't really solve the problem, because if it's difficult to do this, then the plugin authors will make mistakes as well. And that's how you end up with plugins that are buggy or plugins that don't work well together when you combine them with other plugins, which is an experience I'm sure everyone has had before. And this is basically what makes build tools complicated. So that's why build tools are hard for implementers and not just for users. And it's not so easy to just make a better build tool. It always starts off simple, but as you try and satisfy all the requirements, you have parallelism, you have caching, you have invalidation, and you have templating. It always ends up being quite a complicated API and complicated system. So next, I'm going to talk about one of my open source projects called Mill. So Mill is an open source build tool that targets the JVM languages, Java, Kotlin, and Scala. So it tries to improve upon the other build tools. It's still quite a young project. It's not 20 years battle tested like Maven or Gradle, but it does have a number of people using it, committing to it, maintaining it. And I know people like Disney or Netflix that use it in small teams within their companies. So mill build files look something like this. So you have a build.mil.yaml in the root of the project. You extend some class and override the Maven dependencies. Or for sub modules, like this test sub module, it's in a test subfolder with package.mil.yaml with maybe it's a Java test with JUnit 4 support with its own dependencies. So once you have this defined, you can run mill compile, run with some flags, test, show assembly, all the normal build tool stuff. Just maybe a bit simpler than what you've seen from Maven. Like running mill run dash text is much easier than running Maven exec colon java dash d exec.args equals blah. And even the syntax for defining it is a bit simpler than the Maven XML syntax for defining these small projects. Mill also has a programmatic syntax, which I'll show you on the left. So this programmatic syntax is a bit more of a boast than the YAML, but it's a bit more flexible if you want to do custom build pipelines or custom tasks. I'll show you that later. Mill uses Scala as a programmatic syntax rather than Groovy or Kotlin, but hopefully it's not too alien. Like it basically looks like Kotlin, except instead of FUN, you have DEF, and everything else is about the same. So what makes Mill interesting is not where it's the same as all the other build tools, but where it's different. And that comes down to the same three areas we saw earlier. So in terms of performance, to compare these things, we had to find a project that's built using two different build tools that doesn't really exist out in the wild. So we had to make our own demos or examples. So I took the Netty code base, and as a proof of concept, just ported it to Mill, got all the tests passing. Netty has 50 sub-projects, lots of code, lots of Java files, and got all the flags and configuration wired up correctly. And once we got that running, we could run some comparisons. So one thing we noticed when we do that is that just across the board, for all the different comparisons we ran, it's just generally faster to do the same thing using Mill than using Maven, whether it's sequential or parallel, whether it's single module or all the modules, whether it's incremental or clean. Like earlier on, we saw Maven takes about 50 seconds to compile in parallel on my MacBook Pro. And if I kick it off using Mill, kick off this compile using Mill, it's significantly faster. So this is actually, I've actually gone through a log. It compiles the same number of files and same number of modules. We're not dropping anything. And instead of taking 60 seconds, in this case, it took about 12 seconds. So in general, it's significantly faster, even though it's doing the same thing, not because we did any magic, but just because we keep the JVM warm, we have more aggressive parallelism, more aggressive caching. We don't force you to clean install so much. So you don't need to create jars and just unpack later. And that results in quite a 4 to 6x clean performance improvement and even bigger incremental performance improvement for small changes. Gradle has a similar story, although the numbers are smaller. So Gradle, we are maybe 3 to 4x faster than Gradle. So Gradle is significantly faster than Maven, and Mill is just, again, faster still. So that's the performance angle. There's some other things I won't go into too deeply. Mill works quite well for bigger code bases in many sub-projects or sub-modules. It has automatic build profiling and see where time is going when you run these commands. And there's selective testing. So if you do have a pull request, you can ask GitHub Actions to only run the stuff that's affected by your code change rather than running all these unrelated tests that you may not care about. So next I'm going to talk about IID support. So I think where Mill is different from Gradle or Maven is that the IID support actually works. So over here, I have the build config for the Mockito error-prone submodule on the left, and the Gradle build config for the Mockito error-prone submodule on the right. So the first thing you realize is that they look about the same. Like they all have the same flags, same Java C options, same dependencies on error-prone test API and JUnit and auto service. So Mill's a build tool, it still needs to do all these things, so we still need to configure it the same way. Where it differs is that where Gradle is configured using these global mutable variables like appending to JVM args or appending to compiler args. And just because we wrap them in a getter and setter doesn't make them any less global or any less mutable. Mill is configured using these method definitions, which are overrides. And where IDEs are generally very poor at navigating around global mutable variables. If any of you use global variables in your application code, I'm sure you get the same experience. IDEs are very good at navigating up and down these method calls and class hierarchies. So for example, I can ask for the docs, and IntelliJ can find the overridden method and give me a docs for the overridden method, so I know what this thing is. IntelliJ can tell me where the overridden method is. I can jump to it. I can see the value that was there before. So it's not just telling me that it's a sequence of strings, but I can tell it's an empty sequence of strings in this case, and other cases may have some other values. And I can find usages. So I can say that, okay, I'm overriding this method. How does this affect the rest of my build system? And here I can see, okay, affects the run module, affects the tests, affects Kotlin code coverage, affects Scala and Scala native. If I just want to search in this file, I can see that fork args gets used in runner gets used in run background task and run fork task, and run fork task gets used in run. So even if we didn't know what fork args is, and even if like ChatGPT is hallucinating or Google's not giving me answers or Stack Overflow is out of date, you can just navigate around in your IDE and just figure it out yourself without having to rely on just memorizing it or having some AI system memorize it for you. I show you navigating downstream, you can go upstream as well. So let's say I don't know what final main class is, or maybe I do know what it is, but it's behaving strangely. I need to find out more detail about where it came from. And let's say it has no documentation. So in many other build tools, like in Gradle, you'd be stuck. If something has no documentation, you jump to it, you end up with you hit the wall. But in Mill, you can just jump to it and see the implementation. See, it delegates mostly to this final main class opt thing. Maybe you don't know what that is. Again, no documentation. I can jump to it. No docs, but I can see it delegates this main class, which is any explicitly specified main class. If there's one, it uses it. If there's none, it calls all local main classes. If there's zero, it says an error. No main classes found. If there's one, it uses it. If there's multiple, then it reports a different error saying we found multiple main classes. Please pick one explicitly so we can use it. So what's interesting is not that this is a new experience, but what's interesting is this is the experience that everyone gets every day in their application code. In application code, you can never get as much documentation as you'd like. You usually cannot ask ChatGPT because it's a proprietary code base. Google doesn't help, it's not on Stack Overflow. But nonetheless, you can always find your way around using an IDE. And in Mill, because Mill is built around methods and overrides and method definitions and classes, rather than built around global mutable variables like Gradle or Maven, it means that your IDE can help you navigate around your Mill build just like you navigate around any application code base. And so you never get stuck just because you forgot what this method, what something does in your Mill build. You can always dive into the code and figure it out yourself with the help of your IntelliJ or VS Code IDE. So that's the IDE support angle, which I think is quite interesting. Last, I'm going to talk about usability. So again, there are two areas. One is to just getting started experience. Earlier, I talked about how getting started with Java can be quite a pain in the neck, so much that people don't want to do it. You have a small Java program and you just can't figure out how to run it without copy pasting from Stack Overflow. And with Mill, it's a lot easier because Mill supports single file scripts out of the box. So I can add this build header to the top of this file to say that this Java file has this build config. So you saw the YAML config earlier on the build.mil.yaml. You can also add it at the top of the file as a header comment. And then you can just directly run this from your terminal, doing ./mil, scraper.java, and pass in the arguments. Like I'm from Singapore, so Singapore is a starting article, and maybe def equals to 1. So I can show you this live. Where is this? Here it is. So if I go down here, go java-script. So over here is my small Java application, single file. There's nothing else in this folder. Well, there's the test suite. And I can just say ./mail HTML scraper .java. Okay, it asks me to pass in the start article, pass in the depth, and it just runs like that. So it's very convenient. You can even have test suites that work like this. So I can do ./mail HTML scraper test.java. And in this case, this small test suite also has a header comment. You can see extends JUnit4, so it has JUnit4 support. And it depends on this HTML scraper.java file. It's the thing that's being tested. In this case, I run a single test and make sure that the Wikipedia page for Singapore contains Southeast Asia and Singapore Airlines. It prints out it found 880 links. So that's getting started experience. I think it's much easier than traditional Java build tools. The large scale customization experience, I think, is also better. So where most build tools require your extensions to be published as plugins, or you need to learn some plugin API to customize your Java, your Maven or your Gradle build, that's just write code to do the thing you need to do. So for example, let me show you this live. So over here, I have this minimal mil build for a Java project using a programmatic syntax. So this means that the foo subfolder is a Java module. When I say extends, that means I get all the methods from that module and I get all the defaults. So default compile step, default source folder, default resource folder, all that stuff. But let's say I didn't want the defaults. Let's say I wanted to count the lines of code in this module and write it to a resource file, like what we saw earlier. So in Mail, the way everything you want to do is a task. All the tasks are methods, and using the programmatic syntax, methods are defined using def. So like def line count equals task. And I can call other methods within here, such as foo dot, one of the source methods. If you're not sure which one, again, the IDE can help you. In this case, maybe I want all source files, which is all individual source files fed into the Java compiler. Map each file to the file path. Read the lines, dot size, and sum them up. And that's all I need to do to define a custom task in Mail. So I'm just defining a method that calls another method and does some processing on the value that the method returns. So now if I go to this in the terminal, I do ./mail show foo.line count. You'll see that, okay, now the line count is 17. I can do mail inspect foo.line count. You can see that it automatically captures things like the Java doc for you, so you don't need to put into a string like you do in Gradle. It automatically captures the input tasks for you, so you don't need to separately say register task input or task dependency. Just when you call the task, it knows that you depend on it, so it just does that for you. So this is all you need to create the task, but I haven't yet created our resource file. So in Mail, resources are tasks just like everything else. And again, tasks are methods. And the way you customize a method in any object-oriented language is you override it. So I can say override def resources. Again, you're not sure which one. IntelliJ can tell you which one. I want this one. I call super.resources. And I'm going to write to my task.destination folder, which I'll explain in a moment. .txt, my line count as a string, and I will append this to a reference to this to my resource path. So what's this task.destination folder? So the problem this solves is that in any build tool, the file system is like the world's biggest global mutable variable. Like anyone can read and write anywhere in your target folder. Generally becomes a big mess. You can't safely parallelize things, so you don't know who's using what file and who will stomp over the same file or who is requiring the file you're trying to delete. So with Mail, we say that if I say mail show foo.resources, every task gets a destination folder that's unique to that task, and only that task can write to. So in this case, my super resources is here as the original foo/resources folder. We didn't throw it away. We kept it. But I added on this new in the output folder, out/foo/resources.dest, which is this task.destination folder. And the contract here is that every task can only write to its own folder and can only read from other people's folders. So that rather than having this big global mutable file system that can get really messy for humans and for the tool, we're encapsulating the mutability to these nicely encapsulated, locally mutable file systems that are globally read-only. And that really helps manage the tool a lot, helps manage this mutability a lot better. And now that I have this, I can do mail show, I can just do mail foo.run. And see that you can print out the line count 17 using the file system resource that I generated at build time. So if I cat out /foo/resources.dest, slash line count.txt, you can see I generated this 17 file at build time, and I'm now using it in my runtime application. So this is a bit artificial. No one actually wants to count lines at build time and print it out in your production system. But it just shows how easy it is to customize your mill build when you want to make it do something. So we don't have any mill line count plugin. We don't have any mill exec plugin or mill resource gen plugin. You just have your mill module class, and like any other class, you get methods when you inherit the class. And you can define your own methods that call its methods. Or you can override its methods, call your own methods, and call super. And all of these are things you already know how they work. Like the syntax may be a bit different because it's Scala rather than Kotlin or Java. So use def rather than fun or public static. But the semantics, you all know object-oriented programming, and all we have to do here is write quite a boring object-oriented program in order to customize our build to do whatever we want to do. In this case, it might be counting lines. In other cases, maybe running a linter, maybe doing code generation, maybe doing a resource minification. Anything you want to do, you can just write a bit of code and do it in a very straightforward manner. So this example, that's the usability angle. We saw both for small projects, it's easy to start, but also for larger projects, it's very easy to customize and like really wrangle the tool into doing what you want rather than making you do what the tool wants. So I think these is great, but the obvious question is like, if Mill can do this, why don't other build tools do all the same things? Other build tools have been trying to improve their performance, ID support, and usability for decades by now. I think the interesting thing at Mill lets Mill improve upon these areas is this idea of object-oriented builds. So earlier on, we touched on how a lot of the build tool complexity comes from these templated graph computations, and templated graphs are fundamentally very difficult. Like if I try to define a templated graph class, or you try to define a templated graph computation class, it will be a very complicated and hard to use class. But turns out all of us have been working with templated graph computations for many years now, and it's just been what we call object-oriented programming. So that's interesting. Like if you say, when we say object foo extends Java module, you already know that foo gets all the methods from Java module. These methods are called and have data flow between each other. So resources gets used by compile, gets used by class file, gets used by assembly. Resource also gets used by assembly. And I don't need to teach you anything to say that if I say def line count calls resources or all source files and does some processing, or I say override def resources and I call line count and I call super resources and does some processing, writes to a file or something, I don't need to teach you anything about the mill build API for you to know how this affects a build graph, because all of this is a very standard OOP. Like I overrode resources, so assembly now uses a new one. I call super, so the super one is now used by the older one, and line count calls sources, resources call line count. And what's interesting here, I think, is that there's no code here related to dependency tracking, parallelism, or caching at all. So what you don't see is depends on input file, output file registration statements. You don't see threads or locks or semaphores or mutexes. You don't see cache key computations, cache invalidation, cache reads and cache writes. All of that's handled for you more or less behind the scenes. And so from user perspective, you just write what's a very boring object-oriented program, and Mill handles all the rest of the stuff for you. So yeah, so for example, Mill can say that line count and compile can run in parallel because they don't depend on each other. Mill can say that every task has a name, like line count, foo.compile, foo.assembly. And so Mill can use this as a command line name, and also use this to provide a place on disk to put each of these files caches, metadata caches, and files caches. Mill can do automatic invalidation. So you touch the resource folder, it just does a breadth first search. You need to recompute assembly. You don't need to recompute compile and line count. Compile and line count can have their data found at these standard locations on disk because it's always at these standard places. And assembly also has its data found at standard locations. So Mill can go and delete the old data and recompute it from scratch. So this is some of this idea of object-oriented builds. Like in Mill, although there's this YAML syntax and this programmatic syntax, fundamentally Mill builds are about methods, objects, classes, extends, overrides, and super. And these are things that all of you already know how they work. These are things that IntelliJ already knows how it works. So there's no Mill IntelliJ plugin. Mill already knows how all this stuff works, and Mill can navigate around without any help. IntelliJ can navigate around without any help. Mill handles all the other stuff for you, which means that you generally get better performance because you don't get plugins forgetting to cache things or forgetting to parallelize. You don't need a clean because you don't have plugins screwing up the cache computations like your Maven clean installs that everyone always has to do in Java land. In Mill, you don't need a clean because Mill handles the caching for you and generally doesn't screw up. And just makes life easier so you can work, Mill can work on fun features in Mill rather than struggling with these templated build graphs. Can do a bunch of tooling integrations or work on application code. And like on the topic of tooling integrations, we've taken the liberty of integrating a lot of the existing tools with Mill out of the box. As I showed you earlier, extending Mill with custom logic or custom integrations is very, very easy. So if you want, we just want to integrate it with all the linters, all the JVM languages, all the publishing destinations and packaging formats and web frameworks and so on. And if there's something that's not on this list that you want to integrate, like maybe you want to use Quarkus rather than Micronaut or something, hopefully it's not too hard for you to integrate it yourself, like what I showed you earlier. So that's the idea of object-oriented builds. And I think that's where Mill is able to really make a difference compared to other build tools. We didn't just put more effort into ID integration, more effort into performance, but because we have this kind of underlying simplifying idea, that really makes everything a lot easier for us to work with, both for users using Mill, but also for us working on Mill to really make the internals a lot better and easier to improve. So here's the last slide. I won't read it out for you. It just summarizes everything I talked about. I guess the long and short of it, if any of you have ever had problems with your Java build tools and wondered if there's a better way, I encourage you to try out Mill. So Mill's a lot younger than other build tools like Maven or Gradle. It's like maybe 3 or 4 years old rather than 20 years old. But it does have a lot of interesting ideas. And these ideas do translate into really concrete improvements. It is much easier to get started with small scripts or small programs. It is much easier navigating your IDE. It is much faster to run from the command line and much easier to customize when you need to make it do what you want. So the docs for Mill are the millbuild.org website. There's examples getting started with for Java, Scala, and Kotlin. There's lots of docs. So for example, on Spring Boot documentation, there's stuff here. On publishing to Maven Central or Gradle native image documentation, there's stuff here. And if you want migration instructions, there's also some migration documentation with automated migration tooling. So I think that's the end of my talk. Thank you for listening. Yes, any questions? Are there any questions in this chat? Yeah, okay.
Have you tried it for JetBrains plugins? But you said you more than JetBrains plugin before?
I have not used it for a JetBrains plugin. Yeah. In theory, it should work because JetBrains plugins, I know you can build them with Gradle and can build them with SVT for some of the Scala plugins. So in theory, Mill should work, but I haven't done it myself. Am I using WaveTerm? Someone asked. No, because I don't know what that is. My terminal is a vanilla OS X terminal. Yeah, not even iTerm 2. Yeah.
What is the one thing that those the Maven's performance games like
Compared to Maven, it keeps the daemon running, whereas Maven doesn't. That makes a huge difference. Compared to Gradle, Gradle also keeps the daemon running. I don't know why it's slower. I actually haven't figured out. Like in theory, it should be the same. Yeah, and also the parallelism is much better. So Maven has parallelism at a module by module level. So for example, what I showed you earlier, where these two tasks within the same module can run in parallel in Mill, they cannot run in parallel in Maven because Maven can only run parallel module by module. So this module can only run one step at a time until it finishes and other modules can start. Maven also has this strange thing where it waits until a module's test finished before it starts downstream modules compiling, which is in theory not really necessary. Like you can compile this and compile that while this guy is testing and compile downstream one while he's testing and so on. But Maven is very conservative. It runs all tests before we start compiling next one. And that also slows things down significantly. Although in this example, it didn't because I use install rather than test. I purposely turned off the test for fairness. Someone asked, can we create subclasses and superclasses as well? And the answer is yes, you can. So if you look at all these things like Java module, these are all classes, and you can create your own classes and extend them if you would like. I have one example here I touched on briefly, but for example, if I want my line count logic to be reusable, I can put into a reusable class, or the syntax is called a trait for some technical reasons, and I can extend it in multiple other objects and reuse my reusable logic. And if you want this to be usable by people outside your team or organization, you just publish this class to Maven Central like any other project, and they can pull it down and use it within their own projects. So it's really just classes and methods and objects all the way down. Cool. I guess we are done.